Okay. So now let me talk about the next topic that I wanted to address, which is called as linear transformations. Okay. So whether a transformation made, whether it is linear or not. Okay. So I came across questions in question paper also. Here there was one question. Okay. There are two variables, by the way, x, y. Okay. In two dimension. Now the vectors, they are making a transformation to R2 to from R2 space to R3 space. How? So the first one is x minus y, second one is x plus y, and third one is 2 multiplied by x. Question they are asking is whether the transformation is linear or non-linear. Okay, so let me, to in the beginning itself, let me put a question here to you people also, that whatever the next topic that is going to come up, you are going to try, instead of 2 into x, you also try 2 plus x. Okay, I expect you to try a question wherein you have an x minus y, x plus y, and a 2 plus x instead of a 2 multiplied by x after the end of this particular discussion. Okay, by the way, how do we need to check this? There are two conditions which you need to check. This is similar to what we have studied in system properties. What are the properties of systems? Can be linear, time invariant, causal, stable, memoryless. Remember? Okay, there we have studied linearity. So here something similar. There we have found out that if at all there is a transformation, if constants get added, then they are going to be non-linear transformations. Anyway, and the requirement is, if at all you have the transformation, then addition of individual transformation should yield you, okay, the resultant of addition of both the transformation. And second one is transformation of the scaled individual entries shall yield you a scaled version of transformation. Okay. So these two condition needs to be checked. Okay, let us try them. Okay, so here let me go to next page and let me clear all my drawings here first. Okay, so what I will do is, how do I check this x and y? Okay, I already have an xy. So what I will do is, in this particular case, let me take an x1 and okay, let me take an x1 and y1. Then let me take an x2 and y2, because the first condition is transformation 1 and transformation 2. Suppose there are transformations, one applied to one set of x and y, and that applied to another set of x and y. So I took first set is x1 y1, and the set is x2 y2. So when I apply to x1 y1, I will get x1 minus y1, x1 plus y1, 2 into x1. When I apply to the set x2 y2, I get x2 minus y2, x2 plus y2, and 2 into x2. Then if at all I add them, they all get added up neatly and it all works fine. Okay. And second one is scaling by factor C. Okay. Let me take, okay, I will take the scaling factor inside. Okay. So what's going to happen? X minus y, get scaled by C. This also scaled by C. This also scaled by C. And both of them work nicely. So first equation matches with second equation. Here also first equation matches with the second equation. Transformation is linear. It will be more fun if at all I take, what did I tell you? Had I taken 2 plus x1. If at all I taken this as 2 plus x1, this would have been 2 plus x2. Okay, this would have been 2 plus x2. Together, they would have yielded me x1 plus x2. They would have yielded me x1 plus x2. Okay, it would have x1 plus x2 plus 4. Okay, they would have yielded me x1 plus x2 plus 4. Whereas when I do this particular thing, then what do I get? Then I will get 2 into, okay, 2 plus x1 plus x2. In this particular case, I will get 2 plus x1 plus x2. Whereas in this particular case, what I will get? I will get x1 plus x2 plus 4. So equation 1 and equation 2 will not be same, and the transformation will turn out to be non-linear. Okay. So that's a hint. Okay. Observe them. Okay. If at all they are, being operated by linear operators like addition or multiplication, subtraction or division, then it is going to be a linear transformation. The moment, if at all, there are constants getting added, log transformation or even quadratic transformations, x square, e to the power x. Okay, the moment you see any such transformations, then such transformations are going to be non-linear in nature. Okay, so this is one topic which I wanted to address, linear transformations. And as I told you, what the equations very carefully. You can see here multiplication and addition. The transformation is going to be linear. The moment you see the cases which I told earlier, then the transformation is going to be non-linear. Okay. Now let us go to the next topic which I was interested in, that is linear least squares. Okay, this topic it came under projections. Okay, so let us take this particular simple fun example here. What is this particular thing? Remember the case which we always used to discuss, that of a pen and a pencil. Wait a second, let me take you to my MATLAB screen. Wait a second. Where is it? Okay. Let me take you to this particular MATLAB screen. I hope you can watch this particular thing. Okay, you remember this very example of a pen and a pencil. Okay, I give this particular, keep on giving this particular example. What is it, by the way? If at all there is one pen, okay, one pen, 1x plus two pencil. If at all you go to a shop, buy one pen and two pencils. Okay, the shopkeeper charges you 18 rupees. And if at all you take two pens, okay, if at all you take two pens and two pencils, and say the shopkeeper charges you 28. This is an equation. Okay, this is an equation where the matrix, okay, this first particular thing, the one matrix becomes 1, 2, 2, 2. Okay, and the matrix B becomes 18 and 28. Okay, there are how many unknowns? X and Y are unknowns. Two unknowns and two equations. Fine. Okay, two unknowns, two equations. Fine. Okay, things all work out. But then, what if at all you have, if at all you have two unknowns, you need how many equations? Two equations. If at all you have three unknowns, how many equations do you need? Linear equations. You need three independent linear equations. Okay. If at all there are three unknowns and you have only two equations, then it's a crippled situation and there are several solutions, right? Or there cannot be. Okay. That thing happens. Imagine a situation where you have only two unknowns, but if at all you have three equations. Okay. Now here is one such situation. Unknowns are two, but equations are three. In that case, what you will do? Such systems are called as overdetermined systems. Okay, such systems are called as overdetermined systems, and it is very less likely that you are going to get the proper answer. Okay, so let me try it here. This is an example of an overdetermined system where you have equations. You can see A contains, what is the size of this A? Now let me come here, let me type this A. See here, A is 3 cross 2, okay, and B is also 3 cross 1, but the number of unknowns here are only 2. In this particular case, the classic theory of you having to find this A and B. Now see here, if at all I want to find this A, so what is the usual solution? You are trying to solve this Ax equal to B, right? You are trying to solve this Ax equal to B. One of the usual method is finding an inverse, multiplying by inverse with B. So see here, I multiply inverse of A with B. Let me try this with this one here. Okay. Did I tell you this pen and pencil example? A proper example, two unknowns, two equations. Okay, now see, this is my B. And C, by the way, is the values. And if at all I want to know, now you might have guessed what is the price of pen and pencil. I have kept it same, by the way. It's last year, okay? 10 rupees for pen, 4 rupees for pencil. It worked because inverse of B was existing and it was working fine, right? What is inverse of B? That's how we found it. Okay. There are different methods. Even you have tried row reduced echelon form also. Inverse of B existed. For this particular case, by the way, where there are two unknowns, but there are three equations. Okay. Now we are complaining that, not enough data, not enough data. Here's the problem is we have an overdetermined system and we are in trouble. Now see, the first problem that you are encountering is inverse is a situation. Matrix must be square. Okay, that's what MATLAB said. Okay, inverse doesn't exist. So how do we get an answer? Will row reduced echelon form help? Definitely not, because shall we try RREF of RREF row reduced echelon form of the augmented matrix, which was A and B, right? You can see 1, 1, 1. Oh, wait a second, wait a second. Okay, okay. Okay. RREF of what you should have done? A with B. I don't know. This answer, by the way, is not so convincing. Remember, this answer is not so convincing also. Okay. So what should we do now? What should we do now? So these kind of systems, by the way, are called as overdetermined systems. Okay. Now see here. This was it. Okay. And if at all I do RREF of this particular thing, did I get the correct answer, by the way? Did I get a correct answer? We only framed the question, no? So we know expected answer. But see here, it turned out to be, which is the price of pen and pencil. Here you are supposed to have the price of pen and here you are supposed to have the price of pencil, right? And you got both of them as 0, 0. Okay, strangely. So both the methods do not work. Okay, now let's go and see what is the solution here. What is the solution here? So basically what you're trying to do, okay, where, yeah, in PowerPoint. Okay. So how do you solve this? So such systems are called as, by the way, overdetermined systems. And the idea, by the way, is, now imagine how a 2 cross 2, okay, how these kind of systems would work. So the assumption is on an XY plane, usually you have first one, okay, the first condition turns out into a line, second condition turns out into a line, and somewhere at some point they intersect. At some point they intersect. Okay. So there are two lines. Of course, they will intersect and you'll get the value if at all it exists. If the lines are not parallel, it exists, it all works fine. Whereas if at all you have, say on an axis, if at all you have line number 1, say line number 1 and line number 2 and say line number 3. Okay. Now we are here trying to find, okay, see those lines did not coincide, right, at single point. Okay. That's a problem with an overdetermined system. Okay. And what to do? So we are trying for somehow pick a point somewhere in the center, which is going to have least errors. Okay. Let us have an answer which is sort of approximate, not actual. Even we know it, but let us, okay, try to have an approximate answer. So how do we do it? What should be our approach? Let us see. Okay. So the idea, by the way, comes from this particular thing called as the least squares solution. So here what we do is, usually, remember, we are always wondering where do we use this derivatives, first derivative, second derivative. Now see here. What author says, you have a problem, ax equal to b, too many equations, but we are trying to find that x, okay, which is going to have minimum error, okay, which is going to have minimum error. So what we'll do is we are trying to minimize that squared error. Okay, suppose ax equal to b. If at all I make a slight error in x, then what's going to happen? Ideally, ax minus b should be equal to 0, right? But then you end up getting certain error because the line is not coinciding, right? You did not get an answer. We try to minimize that particular error. We are trying to minimize square of that particular error. Okay. So here is an equation. Suppose you have m number of equations, a1 b1, a2 b2, a3 b3, am bm, and what you do is you do the squares, you do the sum of the errors, squared errors, and then afterwards what you do the sum of the squared errors. Okay, see, these terms are the error terms. Okay, these are the error terms. Then you set the derivative of this to 0. Then you set the derivative of this to 0 at a point. Now you can see, you know that it is not going to coincide at a point x. So you are taking this small hat or a bar, you are reading that it is not an x exactly, but it is some x cap or x bar. Okay. So now imagine you set the derivative of x square to 0. What's going to happen? You get a 2 here, then ax minus b1, then ax differentiated, you get an a1 here, and am here. This term anyway is going to remain inside the bracket. 2 anyway becomes cancels and goes to 0. Okay. Now see here, a1 multiplies by a1, a1 multiplies by x, a1 multiplies by b1, and so and so. You take all the terms, x terms on one side. Along with x, there is a1 multiplied by a1, am multiplied by am, and so on. So when you solve for this particular approximation of x, which is not equal to x, okay, what you'll end up is, in the denominator you get a1 square plus b1 square up to am square, which is nothing but the dot product of a with itself, or a transpose into a. Numerator, what you get? a1 b1 plus a2 b2 plus a3 bt plus am b. So it's a transpose into b. Okay. So you can, the idea is you can get an approximation, and it's going to be equal to not x but x bar, and can be got by a transpose into b divided by a transpose into a. Okay. Isn't it comforting? Your row reduction could not solve it. Inverse did not exist, but then you are trying to get a value which is almost there, How do you use it, by the way? How do we use it? So here it is. So what you are going to do is, now you did not get an x, but what you got was x cap. What you got was x cap. Okay, it is possible that, so it can be got by x cap is got. Now here is the equation. Okay, so a transpose into a inverse. Remember, a did not have an inverse, but a transpose into a is definitely going to have a inverse. Okay, a transpose into a usually going to have an inverse, then multiplied by a transpose into b. Okay, so this here, by the way, will be the least square solution for ax equal to b, if at all you have an overdetermined system, and its projection onto the column space is a into the matrix. Remember, this is not dot product, this is into. Okay. So that was interesting case where we get more data. Okay, more data turned out to be a problem, and thank God we found a solution also. Okay. So see here in MATLAB, let me simulate this particular thing. Okay. Now see here in MATLAB, I am in MATLAB. So what is the equation, by the way? It is A transpose into A inverse, A transpose multiplied by its inverse of A transpose multiplied by A, multiplied by A transpose multiplied by B. Remember, in the question paper also, there was this problem where they asked you to represent three vectors, as a combination of three vectors. That was this thing. Which method to use? Actually, it is a row reduced echelon form. There was no such topic in the book where you suggested RREF as a means of solving. This method can also be used. Now see here the problem at hand. Okay, this problem at hand, if at all I use this particular values, x equal to a, this matrix is different, by the way. Okay, this is some 1 minus 1, 1, 1 and 1, 2, some matrix with some b. Okay. If at all I use this particular formula, I end up getting some value of x and some value of y. Shall we see how close is this? How close is this? So this is A, and this is the B. Okay. So is it close, by the way? X1 minus x2 should be equal to 1. Is the difference equal to 1? 1.28 minus 0.57. No. Is there sum equal to 1? Is there sum equal to 1? No. What's the third one? 1 plus 2 into, okay. So first term multiplied by 1, second term multiplied by, first term multiplied by 1.28, second term multiplied by 1.5. Okay. Now this one for third equation, I think it is sort of there because 0.57 into 2 is almost equal to 1. And this is 1.28. No. Yeah, that's the problem with overdetermined, system. But then in mathematics, you might have done it somewhere. So many equations will be given. 7, 8 equations will be given, and only 2 unknown variables. Okay. Then you got to find a way in between. So does it work, by the way, for determined system? There, the proper systems, by the way, 2 equations and 2 unknowns. Yes, it does. Now see here. Let me try this for my system, pen and a pencil one. So what was the question which I gave? Capital B, no? Capital B, capital B, capital B, and this one also C. Okay. So evaluate selection 10 and a 4. Okay. So this method works. So actually, linear least squares method, it works for normal systems for which matrices the inverses exist. It also works for overdetermined systems also. Okay. So I think this is also one of the means of solving such equations. Okay. So these were the 3 topics which I wanted to address. Linear least squares, then what was that? Linear transformation, where I suggested you what to do. Take the clues from module 3 of BSP. Then rank nullity theorem. Okay. Third one was rank nullity theorem. If at all you get a doubt anywhere, just message me. Okay. I shall make a video if at all you want it. Okay. So that's it. Let me stop.